So let's talk a little bit about neuroimaging. So when people say neuroimaging, they usually think the first thing that comes to their mind is MRI. If they're in a medical milieu, if they're in a medical environment, they usually think about MRI. MRI, magnetic resonance imaging, actually started out as NMR. Do you know that? So before we had MRIs, we had NMRs. I'm going to make a long list of techniques here. Now, NMR, it's really interesting because NMR in New York, by the way, they call it enema, which is a different medical procedure altogether. But when I was in New York, I remember when I got there and people told me this is the enema machine. I was very surprised initially, but it took me a while to understand what they meant. So it started out as nuclear magnetic resonance, which was the old name or the first name, nuclear magnetic resonance. But because, and you know, nuclear is another one of those tricky words because some presidents pronounce it differently or used to, and because nuclear magnetic resonance is very charged, because the word nuclear resonates with people sometimes with a bad connotation, they decided to change the name to MRI, which is basically the exact same technique. This is really a semantic difference. It really is a semantic difference. These techniques are the same. So nuclear magnetic resonance imaging is basically the same. This shift was more of a political shift, a semantic shift. Today, NMR is something we use for animals mostly. So if you're worried, because animals don't care, you know, if it's nuclear, you know. So usually today, when you're doing, let's say, a particular imaging or a scan of a rat brain, you would use an NMR machine. And usually the NMR machines go higher in field. We'll get to that in just a second. And MRI is usually for humans. So MRIs, if you're coming from a clinical milieu, there's no chance in hell that you haven't heard of MRIs because it's the bread and butter of imaging today. It used to be, some other things used to be the bread and butter before. Do you know what they are? Just throw them at me. What was before MRI? What was very common? CT, which is very important because it contains some of the words that we need to understand. So CT stands for computerized tomography. The word tomography is going to come up and again, time and again, tomography. And today when we say tomography, it's very different from what we mean or what we meant 30 years ago. Tomography today has a slightly different connotation. So computerized tomography. And CT is basically what? Do you know? What is the technique behind it? X-ray. It's just a bunch of X-rays. Okay, so, you know, I don't have to tell you too much about X-rays, I hope, right? So X-rays, you know, you go, you stand, if it's a chest X-ray for, you know, tuberculosis or, you know, something like that, you stand, inhale, you know, hold it, you know, and it didn't work. Let's try again. That's usually my experience with you know, with these kind of things. But X-rays are a technique that has been around for a long time. And when it came out, when Röntgen just came out with X-rays, do you know what the headlines of the German papers cried? What were the big headlines? Do you know? Guess, take a guess. So after he came out with his invention, the X-ray invention, there was an outcry of people in the field and outside of the field, and people who are, you know, talking in general about the meaning and the implications of X-ray. And most of them were, this is the end of privacy. This is what people journalists wrote in big headlines. Why? Because they said now every citizen is going to get an X-ray machine and put it next to his neighbor's wall and next to the bedroom, and they can see exactly what's happening because it goes through materials and it can go through the wall and you can see exactly what's happening there. This is what people were talking about. And it's important to realize that. It's important to sort of think about those sensational headlines back in the day, because this is to a large extent what's happening today with slightly different metaphors and slightly different stories. But I can see when I talk to people that they still don't understand. They still don't understand what neuroimaging does or what it doesn't do in a very similar way to this sensational story. Now, in hindsight, and because we have today enough sophistication, even if you're not an imager, even if you're not an X-ray technician, you know that is ludicrous. You know that even today, if you get an X-ray machine and you put it next to your neighbor's bedroom, you know, assuming that you have an adjacent wall to share, you're not going to have such a, you know, invasion of privacy. Let's think why that is. So why is it that you can't have that invasion of privacy? It has to do with very reasonable or very practical considerations. Cost, you know, radiation, penetration, you know, how much can you penetrate, you know, with these things? And all these parameters, cost, you know, penetration, all these things are still active today. I mean, these are the same parameters that we need to apply to some of the more advanced techniques, and we're going to apply it, and we're going to see when it actually makes sense to be excited about it, and when it actually makes sense to really genuinely, in my opinion, have a sense of like a frisson, like something like we can do something that we couldn't have done before, and when sometimes we will be at a situation to say, so what? So what? So you imaged it, so what? And this difference between, we can actually see something or we can actually understand something that we couldn't understand before, or this other position of, what are you telling me that I didn't know before? That is a very interesting difference, or that's a very interesting distinction to make. And that distinction requires some finesse. It requires some knowledge. It requires some technical knowledge as well as theoretical knowledge. It requires some understanding of the field, and it also requires some understanding of the questions that you can and cannot pose for this technology to answer. And we'll try to sort of get to that as we go. And I'll try to pepper this particular presentation with some historical tidbits and also with some very practical information about these techniques and how we use them today. So from MRI, which has been around for how long, just about, do we know? How long has there been MRI at Harvard? That's how long we've had MRI. So I'm going to you, just about. Yes, more than that. Okay, so we've had MRIs for more than 20 years actually. So the physics of MRI we've known for a really long time, like maybe 40 years. But until they built the machines and they made them good and they made, and they tested it with humans and like all these things. Today we say that we've had MRI for between 25 and 30 years. Okay, so we've had good experience with MRI, good in the sense that we know that it's very unlikely that it's detrimental to your health, at least in the fields that we're using. So when MRIs were introduced, they were introduced at a very low grade. We were not able to generate very high magnetic fields. They were fairly small. Now, the Earth has a magnetic field. This magnetic field is very important for certain animals, like birds that migrate and other animals that do all kinds of interesting things, especially for fish. But when we're talking about an MRI, we're talking about a machine that induces a field, a magnetic field, that is much stronger than that of the Earth. The magnetic field of the Earth we don't really feel, or at least we're not consciously cognizant of it. Of course, if you have a compass, that can detect it a little bit because the compass has a magnet in it. But if you amplify that field, there are ways to do that, electromagnetic ways to create that. When you create that field, it's very important that that field is very stable and homogeneous and all kinds of other words that the physicists, the MRI physicists are using. And we have the technology today to do it. And for a number of years, the standard for using MRIs started at around 1 Tesla. We usually measure MRIs in a field, in a unit field that is called a Tesla. It has to do with the strength of the magnetic flux. We're not going to go into it. So it started at 1. It went up to 1.5, which sort of became the standard. It's like computers. Computers come out. The processor is 386, then it's 486, then it's today it's an i7. That's this. When you go to buy a computer, they give you this is the standard processor today. Or screen size. It used to be a 15-inch, then it became a 17-inch, then it's a 19-inch. Today it's a 24-inch. So when you go to buy a computer, they say this is the screen, the conventional screen that goes with it, and these parameters change as technology changes. So 1.5 Tesla used to be the standard for a while. Today the standard is 3 Tesla. So you can see how the magnetic field is going up all the time. So, UC Berkeley bought a scanner about 4 years ago, 5 years ago. It was just before I moved here. I was actually part of the committee on that scanner. We purchased a 4.5 Tesla scanner, which was amazing. It was amazing that a university would put its subjects in a 4.5 Tesla scanner 5 years ago. University of Minnesota, at the same time, when they heard the University of Berkeley got a scanner for 4.5, they got a scanner for 7 Tesla, okay? Now the University of Minnesota, when they got their 7 Tesla, they said, hold on a second, we have no experience with humans in 7 Tesla. And they said, okay, but how bad can it be? It's just 7 Tesla. And people said, well, what's 1 Tesla? What's one? How does this compare to the magnetic strength of the Earth? And the answer is that roughly for a Tesla, you have to multiply it by 10,000, roughly. Okay, so this is 10,000 times the magnetic field of the Earth, and and you can do the math. So the question is, 7 Tesla. Today, for example, at the MNI, and I'm going to, if you'd like, I can show it to you, although they might not let me bring such a big group to that area. At the MNI here at McGill, we are building a 7 Tesla for human, for use with humans. However, with NMR, okay, we've had 7 Teslas for a while. Because you see, we don't care so much about the rats and the monkeys, and they go through MNR and 7 Tesla, no problem. So when University of Minnesota had the 7 Tesla, they said, this to us was more of a technological achievement to create a magnet that has a magnetic field of 7 Tesla. We will use it mostly for animals. Today, the 7 Tesla that was used for animals at Minnesota is used today in McGill for humans. It's being built right now. So you can see the times are changing. When I started out in neuroimaging, I was in New York. I was first at Cornell Medical School, then at Columbia Medical School. And when I was at Cornell, any woman who would go through an MRI would have to do a pregnancy test. I never quite understood why, but they required all the women to do a pregnancy test because there is a chance, and as you know, the US is very litigious. Now I understand why, by the way. Back then I didn't understand why. Because the US is very litigious, if you go in and later there's a problem to the embryo or to the child, in the US you can sue back 18 or 21 years, I forget exactly. You can go back to your OBGYN or to whatever the medical staff and say, why did you do this to me? And if you can prove it, it's very tricky. So they had all the females go through a pregnancy test, and if you were pregnant, you would not be allowed to participate in research. We're talking research here. We're not talking about clinical scans. Everything that I'm talking about is research. So at some point, as these things progressed, some people, for example, I remember when I was doing 3T at Cornell, they wouldn't let kids go into the 3T. They would only let them go into the 1.5 Tesla. Today, we do kids in the 3T without even thinking about it twice. When I went into the 1.5T when I was a young postdoc, they told me never to close my arms because you lie down on your back. So when you do these scans and MRIs, they're basically done when you are supine. So you lie down on your back like that, and that's the only position that you can do MRI scans. Today, for clinical scans, so this is we're talking research. For clinical scans today, they have created vertical scanners. So today you have vertical scanners where you can actually stand up. You can stand up and you can get an MRI of the knee, for example, an MRI of your heart when you stand up. That's very important because posture changes many things. It changes the way that weight is distributed on your body. It changes the way that the bones touch, that ligaments are stretched, and so on. And as I would argue later, it also changes the way we think and we solve problems and we look at the world. But I'm getting ahead of myself, so we'll get to that in a little bit. So MRI technology is largely meant for supine individuals, people who are lying down. Not only that they're lying down on their backs, but they're supposed to be stone still. Why? Because the technique is extremely sensitive to motion. Now, I don't know when was the last time they were stone still for an hour and a half, but the early scans that I performed required people to lie still for an hour and a half. Today, still, we have scans that require people to lie down and hold still, if not for an hour and a half, for an hour or for close to an hour. That's a very unnatural situation for a lot of people, particularly for people who are claustrophobic. And then you put them into a tunnel that is very, very tight. If you've never been scanned, you basically are going onto a bed. So this is the bed, you lie down. Sometime in the early days, believe me, it wasn't pleasant. In the early days, either we would put a helmet on you so that your brain wouldn't move about. So we would put a helmet on you that would strip you down, and there's a coil around you so you feel like you're in a cage on top of that. And sometimes they would have all kinds of inflatable pillows around you. So they would put your head, and then you would go so that you won't be able to move around. And these are scary experiences for some people. Not for me, I'm brave, but for a lot of people, a lot of people who went through this, it was a very weird kind of experience for them to be in a big machine that has all kinds of clunky sounds associated with it, and they test you for all kinds of magnetic things before, and they ask you, do you have tattoos, do you have pacemakers, do you have cochlear implants, do you have all these things to make sure that you don't have any metal in your body? Because the problem with magnetic fields is you can't smell them and you can't hear them, and they're very powerful, and they get more powerful as you get closer to them. It's not a linear thing, it's actually something that is nonlinear. So as you get closer to it, it gets stronger in some kind of a quadratic fashion. So it's very tricky, and there are many, many problems with scanners in the sense that people forget. People just forget how powerful the magnetic field is. So we've had terrible experiences where a research assistant would walk in with a piece of paper into the scanner room, and the staple from the piece of paper would just fly out and go straight into the brain of the person through the nostrils. It would just fly through the nostril into the brain and get lodged in. And this would be, these would be terrible accidents that were reported in the literature time and again. And a janitor would go in to clean, despite of all the signs. And we say, I don't have a pacemaker, I don't have a cochlear implant. They would go in with a bucket, and the bucket would fly into the thing. And then, yeah, not through the nostril, but it would fly in, and we've had deaths. We've had deaths as a result of these things all over the world, and these are tragedies. I mean, when it happens, these are tragedies, and they're very difficult. It's very difficult to explain it to people, because when you don't see it, you don't hear it, you can't. It's just a very powerful thing, and you don't have a good feel for it. Even when you go through the experience, you don't have a good feel for it because you never pull on something. I had just one experience when I walked into the magnet at Cornell with my wallet, which I still carry, and all my credit cards, all of them got erased. I mean, I couldn't even understand for weeks after why, this one doesn't work, this one doesn't work, this one doesn't work. I mean, I knew I was a poor, impoverished, postdoctoral student, but for all of them not to work and to all of them to be rejected like that, it's a very powerful field that you don't really fully appreciate. And we can talk more about the way that it works, but I just want you to understand that if the standard was here, a few years ago, the standard is now here for research purposes, and it's pushing down constantly. It's pushing down constantly. The fields are so strong that, when you go above 3 Tesla, we often refer to this colloquially as high field, like MRI. We say high field MRI. High field MRI, however, today, 4.5 is not considered high field anymore. 7 is considered high field. These numbers might be meaningless to you, but technologically they're very meaningful. What is the advantage of pushing the field higher? What do you think? Why would people push the field higher and higher? So, when you buy a car, you want lots of horsepower, right? Because, for the same stable, you get more horses. So, why not? But what does it give you? What does it give you to push the magnetic field? Why are people so fascinated with that, do you think? Better resolution. That's exactly the right answer, better resolution. But you see, when it comes to resolution, the word resolution is tricky in its own right. We have at least 2 kinds of resolutions, and later I'll say that there are more. So there are 2 kinds of resolutions that we like to talk about. So one kind of resolution is called spatial. Okay, and it comes from the word space, spatial. So we're just trying to see how small can we see things happening in the brain. So that's spatial resolution. And then the other resolution that we look at is called temporal, coming from time. So the temporal resolution is how quickly do things change that we can capture in the brain. Now, if we're talking about MRI, there is no element of time, because MRIs are taking static images. It's almost like your camera, your digital camera. You look and you take so there's no element of time. If you take a series of them, then there becomes an element of time. But MRI itself is just structural. It just shows you the structure. It is just a snapshot of what is happening there. Now, even with spatial, we have different ways of thinking about it, because MRI itself, depending on how you operationalize the MRI, you can do different kinds of snapshots. You can take different kinds of pictures that would show you different things. A lot of people, for example, when they use MRI, they are doing volumetric studies. Now, what are volumetric studies? Volumetric studies are studies of volume. So, for example, when you are looking at development, you would like to see, how does the amygdala grow? What is the volume of the amygdala when you're 3? What is the volume of the amygdala when you're 4, when you're 5, when you're 6, and so on? Why? Because you have a theory about what the amygdala does, or how it's relevant to other things, how it's relevant to emotion, to the development of emotion, to fear, to conditioning, all these things. So people study the amygdala volumetrically. Another way to study the amygdala is structurally. That's very different from volumetrically, because you're studying the structure. You're not studying necessarily the volume. You're studying the structure. Structure and volume are two different things. As a matter of fact, different scans are often used in order to study volume or to study structure. There's also elements that are related to connectivity. For example, what is connecting to the amygdala? What fibers are connecting? How are they connecting? When are they being formed? And so on. So it's a very rich field that basically looks at, connectivity and things like that. These are all MRIs. In other words, they're static images of the structure, of the volume. And sometimes we actually add other things to that. So it could be of myelination, of gray matter, of white matter, and we have all kinds of technological ways to create contrasts of these images, to develop them in a certain way, to relax them in a certain way, and all kinds of technological things that would go far beyond what I need to impress upon you or communicate to you today. So there's all kinds of things in MRI technology or in MRI research that are called T-star and T2 and T-weighted and all kinds of weird technology that has to do with the physics. But certain things don't change. So for example, let's talk about the spatial for a second. So today we have 7T. Tomorrow we'll have 18T and then 182T. So the question is, what is the spatial resolution of MRI? What is the temporal resolution of MRI? Can we go indefinitely? Can we just keep on going? Can we have a car with 3,000 horsepower? When does it stop? I mean, is there a physical limit to these things? And the answer is yes, there is. There's a physical limit. Why is there a physical limit? Okay, so for that, in order to understand why there's a physical limit to the discovery or to what you can see, you really have to understand the physics. Okay, so we're not physicists, but we can understand some concepts really easily. So here's the concept, and here's how it works. MRI works in a caricature fashion in the following way. We have blood gushing through the brain. The brain is very rich in blood. Blood itself has magnetic properties because it's got a little bit of magnetic materials that contain a slight bit of iron and other things that are magnetizable. When you are breathing, you're taking oxygen in. That oxygen gets into the blood, and the magnetizability of the blood changes when it's oxygenated or when it's less oxygenated. So as a function of how much oxygen there is in the blood, you get different magnetizability. I almost said magnetizability. So it's very important. It's very important to understand that what MRI does in a very broad, brushstrokes kind of explanation for people who are not from the field or largely not from the field. Forgive me, Daniel, for humoring you. It's very important that you understand how it works. It works in the following way. If the blood has a lot of oxygen, the magnetic property is quite different than if it has less oxygen. You can't see it regularly, but if you put the blood in a very strong magnetic field, and if you perturb it, how do you perturb it? So you perturb it by giving it, it's very technological, but you basically give the magnetic field a very strong jolt. The jolt is called a radio frequency wave. So you basically it's a very strong magnetic field, and then you push it suddenly, you just give it a very strong magnetic wave, and you see how long does it take for certain spins or certain elements in the blood, according to some theory of mechanical statistics, how long does it take for certain elements in the blood to line up with a magnetic field? When you have a very strong magnetic field, usually the magnetic particles line up with the field, right? So if you have a magnet, and you have some particles that are magnetizable, they would be attracted, they would be lined up with the field. Every element, every particle, every object is composed of atoms or something, and these spins, we call them spins, are basically aligning with the field. What we do is we put people in a very strong magnetic field, so they have spins lining up with the field, not all of them, but most of them, and then we push all these spins with a perturbation that is called a radio frequency wave, and then we see how long does it take for them to come back to relax, back to be aligned with the field. The time that it takes them creates a picture, and that picture is the MRI, or variations on that particular technique create the MRI picture, and then we get different times or different alignments for different structures, for white matter versus gray matter, for things that are rich in myelin and fat versus things that are not, things that are rich in water, things that are not, and so on. Now, if only the brain was linearly behaving and everything would be good, this technique would solve all our problems. But there are all kinds of problems that have to do with biological tissue that we didn't really expect, or we didn't know until we started messing with MRI. For example, as we get older, our brains become drier. Did you know that? I didn't know that. Until I started doing neuroimaging, I didn't know that. My brain felt as moist to me today as it did 20 years ago. But it turns out that as you get older, your brain dries up. Okay, you lose liquid. And because MRIs are very sensitive to the amount of liquid or the amount of water that you have in your brain, and has to do with hydrogen atoms and stuff like that. Because of all these things, imaging of brains that are drier is very different from imaging of brains that are more water heavy. And that creates a completely different picture regardless of anything. So all kinds of physiological processes that mask and sort of confound all these great ideas, all these great technologies. And if you're doing a developmental study, the brain at 2 years, at 3 years, at 4 years, at 5 years is not just the same brain. The brain is changing. The chemistry is changing. The concentration of liquid is changing. And all these things are creating artifacts and different kinds of results that you would get as a result of the imaging. So it makes all these studies not questionable, but just suspect to a whole array of artifacts that one would need to know how to correct for, and you would need to take it with a grain of salt. And I just mentioned one, in terms of developmental, but there are many, 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 many that we can talk about. It's a very rich and vast field. Now, at some point, somebody introduced a small letter F in front of the MRI. That happened, slightly more recently. So, this letter F changed quite a bit, many of the things that were going on. As a matter of fact, as a result of the introduction of this letter F, the whole status of MRI went down. So today, if you're doing MRI, you're really a loser, because it's only the fMRI people who are the serious people today. Okay, so it's a little bit like my son is 8. He just turned 8 yesterday, and I had a conversation with him, and he said to me, I'm really happy that you're a brain doctor. He thinks that I'm a neurosurgeon, I think, to a certain extent, and I'm trying to not disabuse him of that notion for now. But he's under the impression, he says, I'm really happy that you're a brain doctor because Josh Cohen's dad is a tushy doctor. Now, a tushy doctor, for those of you who don't know, is a GI specialist who has a lot of interaction with the anus. And that's to my son, in my son's view, that's terrible. You've got to be at the bottom of the totem pole to do that kind of medicine. On the other hand, if you are a brain doctor, what is more elevated than that? And he's very proud. And again, if you hear ever in the news that I'm a brain surgeon, now you understand, where it comes from. But it's very important that you understand that the same thing is true here to a certain extent. So the whole power, impetus, or directive or potential of MRI has been largely shadowed by fMRI. The introduction of the word F for functional magnetic resonance imaging, is basically an innovation that uses the same technology. You don't need a different technology, or largely the same technology. You do need a slight change in the hardware, and you do need a lot of changes in the software, but it is a slight change that suddenly allows you to see what is happening in the brain over time. And it allows you to see a particular form of a metabolic change. And that metabolic change has to do with oxygen consumption. It has to do with how things are being consumed over time. And that goes back to the idea that I mentioned before about the fact that when blood is oxygenated and when it's less oxygenated, it has different properties. Now, when we're doing MRI, how oxygenated is the blood is not really important, because we're not looking at blood. We're looking at structures. When you do MRI, you're only looking at structures. Okay? And the structures have spins, and those can relax or not relax, but blood is not the issue. When you're looking at functional MRI, you can actually take a snapshot, an MRI snapshot of the brain, and then superimpose on that a functional image that would come from changes of the blood as a result of a particular cognitive challenge that you're giving the person, or even no cognitive challenge, just let them sit there and relax. Now, this is very important. This is a big innovation. If before we only looked at still images of the MRI that were coming from structures, and the blood played very little, if any. I mean, in some cases it could play a role, but in general it doesn't. With fMRI, the whole concentration, there's a migration from talking about the structure to talking about where is blood being consumed more or less. And as a result, we're getting a particular signal. One common signal that we often compute is called BOLD, B-O-L-D, has to do with blood oxygenation level dependent signal. This is a particular, today we have other ways to compute this, but for many years it was almost the only yardstick that people used. And that has, again, advantages and disadvantages to what you can demonstrate. And the idea is that you can take an MRI, usually a high resolution MRI, which would show you the picture of the brain, and on top of that you can impose some kind of a metabolic change that would show you how much blood has been oxygenated or not oxygenated as a result of allegedly neuronal activity, because when neurons are working, they're allegedly using up oxygenated blood, a little bit like a muscle analogy, which is not perfect but not entirely out of this world. So for many years people have been thinking about that, and there's a whole army of neuroimagers who are dedicated to methodology. They're developing methods. For example, one such person at McGill, his name is Amir Shmuel, and I often get his email and he gets my email because we're basically working almost in the same field, but he's a methodology guy. He does mostly methodological innovation and I do mostly higher brain function. So we're doing quite different things, but he was actually one of the 7 Tesla people at University of Minnesota. So he's like he's trying to push these kind of temporal and spatial things by working with physicists and monkeys and so on, and I'm not interested in that at all. I'm interested in asking certain questions which would be the kind of things that would be interested to this group. You're not interested in pushing these technologies by coming up with patents or ideas of how to make the field higher or so on. You're interested in what kind of questions can it answer? And in order to understand what kind of questions can it answer, you also have to ask yourself, what are the limitations? So one limitation is, how fast can this go? How fast can MRI go, or fMRI? How fast can it go? So in MRI, there's no temporal component, or largely there's no temporal component. In fMRI, there is, because you can see what is a metabolic change over time. So what is the unit of time that you can probe? Is it a millisecond? Is it 10 milliseconds? Is it a second? Is it 40 seconds? Is it 2 minutes? What is the unit of time? Do you know? The limit of theoretical fMRI would be around a second. You can't really push it down below a second. What is the limiting factor? Let's think about what the physical phenomena is. What is the limiting factor? The limiting factor is, even if I had 1,000 Tesla, okay, the limiting factor is, I have 1,000 Tesla of a field, so all the spins are lined up like this. I give it a perturbation. Let's say I give it a very strong perturbation. How fast would these spins line up? There's a time that it takes them to line up. I can't change that time. That's a physical constant. How long would it take them as a function of the field? Even if I have an infinite field and I give them a perturbation, how fast would they line up? There's a physical limitation there. If you do the calculation, and you can do the calculation, people have done that, you can demonstrate that it would probably verge on the second. You can't push it more, even with all kinds of enhancements. You can't go much, much, much faster practically than a second. And even a second is pretty theoretical. It's usually a little bit, slower than that. So and everything that I told you right now is actually one big lie, but we'll change that some other time. So right now, I just want you to understand this level of sophistication. So we are at about a second. If I want to give you a comparison to a different neuroimaging technique that has a different temporal resolution, can you think of something? What other neuroimaging techniques do you know? Sorry? PET. Okay, so PET is a great one. We'll talk about that for a little bit. So PET stands for positron emission tomography. Okay, and positron emission tomography, unlike MRI and fMRI, is an invasive technique. It's a technique where you're still lying down supine and you're still going into a scanner and you're still in a tunnel. All these things are very true, but in addition to that, you need to have an IV line in. And in that IV line, you're getting usually some kind of a radioligand, a radioactive material. And that material, either radioactive sugar or radioactive oxygen, would actually bind, okay, or would travel into your blood and go into your brain. And then we have all these, again, the same T. This T and this T are the same. tomography, and tomography just a fancy word to say we're going to take plenty of two-dimensional images and make this into a three-dimensional rendering. So that's the tomography that we're talking about. So there's a particular physical experience or physical phenomenon that we're exploiting here, and that is that when you have a radioactive material in your body, it decays. And if you know the half-life the half-life is how long does it take for it to have half the material that was there before. So radioactive materials are very unstable, and when they're unstable, they emit all the time radiation. And these particles that they emit could be measured. Actually, they're being measured all the time in Iran and other places. We want to see how much of them are being transmitted, and from that we can conclude how much was there at the beginning. And you can say, based on when I measure it now, I know that 5 years ago you had here this amount. You can actually go back. This is how you look at archaeology sometimes. You can tell very accurately when something was happening based on the half-life of a particular particle or compound. So once you inject them with a particular amount, now you have to be very careful. You can't give them too much. You need to give them a minimum amount, and it has to be very, very fresh so that you can count how much is loose. So people usually who are doing PET have a small, sometimes a large device called a cyclotrone on the premises. And the cyclotrone prepares, it's a big physical device that actually prepares the radioactive ligand that you're going to use in your PET. So as you can see, to do a PET study is quite complicated. A, it's invasive. Okay, B, you need a cyclotron. And right after you make it into cyclotron, you have to run very quickly and inject it to the person, because the second you prepare it, it starts decaying. So let's say that I ordered some radioactive sugar from Amazon.com. So by the time it comes to me, okay, so let's say they send it to me FedEx, okay, Purelator. So they send it to me very quickly. I start running towards the PET scanner. I get the envelope. I open it up and I immediately inject it. It's ridiculous because the time that it took from the amount that is left in the thing is zero. We're trying to create so that the person in the scanner would have minimum exposure to radiation. We're trying to create elements, radioactive materials that are very, very low radiation so that we can inject them. So we create them in such a minimum dose that when we inject them, we can have just the trail end, and we can from that surmise what's going on. If we give very strong things, we don't need that. We can send people to Japan or other things like that and do these kind of studies. Not nice. So it's very important to understand that this is a big operation. It's not enough to have a PET scanner. You need to have a cyclotron as well. You need to have people with nuclear medicine expertise. It's a big deal, as opposed to an fMRI when you don't need that stuff. Sometimes it's enough to have one MRI physicist. Sometimes you don't even need that, depending on where you're working. So this is a much bigger operation, but the questions that you can answer or you can ask with PET are very different from the questions that you can ask with fMRI. How? Why? Because this is a very different process that calls for a very different temporal resolution, and this is exactly what I was trying to make. What's the time resolution of PET? Do we know? More or less. So when I said 1 second for MRI, I was very kind to fMRI. But what is the time resolution, the temporal resolution of PET? Do we know? Let's think about what it does. Okay, so you're injecting, the thing goes up into the brain. The person is supposed to engage in. This is not PET for identification of a tumor, like cancerous tumors or something like that. This is PET in order to see cognitive activity in the brain, not to confuse the two, the completely different things. This is not a clinical scan. This is a research scan. So the blood, the radioligand-rich blood goes into the brain, and we would think, because it's equally distributed, we would think that neurons that are working more are going to take more of that blood, and therefore they're going to shine more radioactively on the sensors. So those areas are going to shine more, and we're going to say, aha, those are the areas that are working when the person is solving this problem or thinking about this thought or engaged in this particular thing. Do you understand the theory? Now, the way that this works requires, do you have a guess for the temporal resolution of PET? Take a guess. Sorry? A millisecond. It's much slower than fMRI. I'll explain why, but it's much, much slower. So I would say that if you want to just get a good number, 35 seconds. 35 seconds to 40 seconds. So you would need something to happen in the brain, okay, for about that long in order to see something. So let's say that somebody comes to me and says, I'm a memory researcher. Sometimes it happens to me, by the way. I'm in a cocktail party. I've had one cocktail too many, and I'm a little bit loose. And somebody comes to me and says, I'm a memory researcher. I say, oh yeah, that's pretty cool. What do you do? I do PET scans. What? How can you do PET scans for memory research? What kind of memory are you researching? Are you trying to see how people remember things in 35 seconds? What are you trying? What is the process? What is the process that you can elucidate with a PET scan when it comes to memory? I wonder. Do you understand? Memory is one of those things that happens very quickly. Like if I ask you, do you remember da-da-da-da-da? If it takes you 35 seconds to remember, sometimes it can happen, okay? Sometimes it can happen, and sometimes it would take you weeks. Dry brains, yes, the dry brain syndrome. But you have to understand that by and large, so there could be some very unusual situations where you would use a PET in order to study memory, but in general, it doesn't sound right. There's something very wrong. It's like somebody. I said to somebody, what do you do? I'm a speed car driver. I'm a racer. And what do you drive? I drive a tractor. It's like there's something incongruent with these kind of things. So now to a regular person, it doesn't sound like anything. Oh, he's doing neuroimaging, he's doing PET, But if you begin to understand the technology and so on, you begin to have a better finger on the pulse. This is a slow thing. This requires something that happens over time. It requires some kind of and some cognitive processes happen over time. Some things happen over time. And you can do that. Okay, so if you're looking into something like pain, that is chronic or something like that. There are many things, including some cognitive phenomena we can talk about that are happening over time. But the temporal resolution is very crude. How about the spatial resolution? The spatial resolution of PET. What about it? What about the spatial resolution of PET? So is it better, you think, or worse than fMRI or than MRI or fMRI? Well, that's a very tricky question because I didn't really tell you how this is done and the physics behind it. But the fact of the matter is that it's much cruder. It's much cruder. Okay, so your ability to see what's happening with PET in terms of a spatial resolution is lower, and in terms of a temporal resolution is lower. So a lot of people, that's enough for them, and they say, I've heard enough. I'm just going to do fMRI. Because PET is for the birds, because the spatial resolution sucks, the temporal resolution sucks, and you need the cyclotron, and who needs all that headache? But you see, this is where the mistake lies. It's not that one is better than the other. It's about the question. What kind of question are you trying to answer? What is your question? These are just tools. One of the common mistakes, these two guys over there, Michael and Eli, have taken one of the courses that I take on neuroimaging here at McGill, and I start that class by saying, I can't take it anymore. People come to me, knock on my door, and say, I want to do fMRI. I feel like taking out a machine gun and going, what is this thing I want to do fMRI? What's your question, man? What are you trying to answer? It's like saying, I want to ride a bicycle. Okay, ride a bicycle. It's a tool. It's a tool. You need to understand, this tool doesn't answer all the questions in the world. It's a tool, and you need to understand how to use a tool. If I give you, a piece of chalk, you can write on the board. You can do all kinds. You can eat it. You can do all kinds of things with it. But the question is, it's a tool. How do you use it in order to answer a particular question? And today, people have been so fascinated with the technique that it became the goal. The goal is to do fMRI. They're completely confused about what it does. And you have to understand that there's certain things that it does very well. It can answer some questions really well, and some questions it has no bearing on whatsoever. But the thing is that even if you take a question that has no bearing on, and you'll do an fMRI, you'll still get results. You'll still get brains that light up. It's crazy. That's the crazy thing about it. You can take a design that is meaningless. You can do an experiment that has absolutely no rhyme or reason to it whatsoever. You can even put a dead salmon in the scanner and you'll get something. You'll scan and and people have done that and published that too. Okay, and they show that you can take these kind of meaningless paradigms and something comes out, and then people look at it and say, wow, look at this, it's in the brain. And there's something, inherently wrong about that kind of thinking, because they just don't fundamentally understand what these things can give you, what their shortcomings are, and what their relative merits are. And they have relative merits as well as shortcomings. But it's not something that you can walk into and say, do it. I just shared it with Lawrence. A few days ago, a particular company contacted me with a particular research question that they wanted to answer, which is meaningless, completely meaningless question, but they're willing to pay money for it. So, sometimes you become a prostitute, in science. That's true, and I felt it recently, in a very compelling way. But it's very important to understand that when it comes to these things, you need to have a particular sense of sanity about this. Like, what can you do and what can you not do? You're going to get something no matter what. Whatever you do, you're going to get something. Now, what is the meaning of what you got? So the design is very important, and the question is very important, and what is the theoretical implication is very important. These are very important things, but you need to understand also, some of these things. So PET is one thing. We have a PET scanner here at the MNI. The MNI, by the way, has one of the largest collection of brain toys that you can find in a big radius around here. Because it's got a farm of toys, very expensive, and all of them are at the disposal of brain researchers from McGill, because historically it's a very strong neuroimaging, one of the premier neuroimaging centers in the world, and they're trying to maintain it. It's very important that you understand that PET on its own is powerful, but PET with fMRI could be even more powerful. And if you put TMS together with it, could be even more powerful. And if you add ERPs to it, could be even more powerful. And if you add EEG to it, it can be even more powerful. And all these are, techniques. You have, optical imaging. So let's talk about these things a little bit, just so that we can, now that we understand, some of the parameters that are going on. And we need to understand, what's going on here, because these are all imaging techniques. And there are more. There are others that I'm not even mentioning. Because within MRI, there's a whole, spectrum of things that is called where you can do a manipulation on what's going on. So for example, one of them is called DTI, diffusion tensor imaging, which actually has to do with connectivity, and the issue of water becomes even more important there, and so on and so forth. We're not going to go into it, but I just want to show you it's a vast field. And the trick is to know what you're asking. So for example, optical imaging. Optical imaging is very cheap. I can probably get you an optical imager for just a few $1,000s, sometimes even less than that. But it's also very cheap in terms of the questions that it can answer. So how does it work? It's basically a beam of light, not necessarily visible light, but a beam of light that you basically shine into the head through a skull, and then there's a detector that you put, next to it, and the light goes in. Some of it is being swallowed, some of it is being, deflected, and you're basically looking at the reflection of the light, how much has been absorbed, how much of it has been, coming out. And this is not something you can do with your bare eyes, that you do it with very, sensitive sensors, and allegedly, based on the light that has been absorbed, you can say something about the activity of the brain. This is a very crude method, but it works. It works if you're interested in information right here, behind your forehead. Okay, it's going to be very difficult to shine light over here and learn something about what's happening here in the back, because there's going to be a lot of absorption and a lot of junk in between these 2 points. So you say, okay, so I'll come over here and I'll shine it over here. Yeah, you can shine it over here, but then the question is, what kind of information do you have to compare it to, and where's the anatomy and all? This is a very tricky field. People do optical imaging and they do it successfully, but you need to have a very, very specific way of asking the question, and you need to know exactly what you're looking for, and you need to have to maybe combine it with MRI in order to make sure that you are on the right spot, and so on and so forth. So optical imaging is something that is a little bit on the rise. It's almost as crude as pupil dilation. It's just a marker to show that something is happening. It's very difficult to say exactly how much. Let's put some price tags on it so that you understand how much these things cost. How much is a PET? Do you know? Million? So a PET is usually around 3 million, about 3 million, just about, okay? And a cyclotrone is much more expensive. So I'll give you the PET for free if you give me 6 million for the cyclotron. I'll throw it in there, 2 for 1. But just so that you understand. And to have a cyclotron, by the way, you need a chemistry department because they need to, you need nuclear medicine because they need to manage, radioactive material. So you need the whole facility. It's very expensive. How much is MRI? How much is an MRI, more or less? Okay, between 2 and 3. Usually a good MRI between 2 and 3. Okay, 2 and 3 millions, just about. I mean, sometimes you need to do some installation and stuff like that. That costs a little bit more. How about ERP? Do you know what ERP is? ERP EEG? Okay, so ERP EEG, very simple technique. Very simple, has been around for, since the 40s basically, even 30s, but 40s. And basically, you take an electrode and it serves like a microphone. So you take an electrode and you put it on the head. And let's say that I'm interested in listening to what's happening next door. I can take a microphone, I can put it on the door. And then whatever is happening next door would vibrate the door a little bit and I'll be able to hear what's happening next door. Now, if somebody's playing the tuba next door, I probably don't need, an electrode. I can hear it. But if somebody's speaking very softly, I might need amplification. So I put the microphone on the door, and I connect it to an amplifier. And then the amplifier amplifies even the smallest thing. So there's going to be some noise, there's going to be some, but I can then go into the information, amplify it enough, remove the noise, and I might have a signal that I can listen to. Particularly if that person repeats what he's saying all the time. If he says, hello, 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 hello. So I collect all these things repeated, I clean the noise, I superimpose it one on top of the other, and I get some kind of a canonical hello after a while. So he's trying to say hello, I guess, from what I'm hearing. So today, at the beginning, we took all these electrodes, we put them on the head, and we eavesdropped to the collection of electrical activity that emerge. And that cacophony, when it's happening spontaneously, is called EEG. So if you just put electrodes on the head and you're just listening to what's happening spontaneously, that's just EEG. And that EEG is actually indicative or somewhat indicative of some kind of a mode of activity or baseline mode. So for example, we can see different EEG in people who are sleeping, people who are concentrating, people who are tired, and so on. And sometimes people classify it as alpha waves, beta waves, and delta waves, and things like that. And we have bursts of activity, and we can localize it to a particular area. So there's a very rich literature on EEG. It's been around for a while. ERPs is EEGs with a twist. So if you add a little bit of lemon to EEG, you basically get ERP, which is basically an EEG system that allows you to now connect or relate the EEG to a particular, to lock it in time, to lock it in place, to a particular cognitive challenge. So now the person is actually solving a problem or performing a particular task. And when you do that, so now it's not spontaneous, now it's relative to a particular task. And when you do it relative to a particular task, you can actually see what's happening specifically, and you can look at all kinds of electrodes. When we started doing EEG and ERP, we used one electrode for grounding, which is like the baseline or the base activity, and 2, 3, 4, 5, 6 electrodes for collecting information. Now, you already know, or you already see, just from listening to me, that there are many, many, many disadvantages to ERP. What are they? First of all, it can only eavesdrop to activity that is very close to the skull. It can't pick up very accurately information that is deep subcortical or in the thalamus or very deep inside because it's far away from the microphone. The further away you are from the microphone, the less you're going to be able to hear. Clear? Yes? The other problem is that each electrode is basically listening not to one neuron, not to 2 neurons, not to 3 neurons, not to 4 neurons, not to 1,000 neurons, not to 10,000 neurons, not to millions of neurons. Each electrode, when you place it on the head, is basically eavesdropping to the activity of millions of neurons. It's very difficult to figure out what's going on when you're listening to millions of neurons. So basically what you're getting population signals. You're getting signals that are from populations of many, many millions of neurons, and you need to average them, and you need to do all kinds of crazy things. When it comes to crazy things, by the way, it's very difficult to top MRI and fMRI, because that's when craziness rules. But we'll get back to that, a little bit later. So how much is a system like that? Okay, you can get a reasonable system for 30,000. You can get a deluxe system for 150,000. and then all the peripherals and stuff like that would cost you about double. So between 30 and 150,000, you can get a good system. We have deluxe, creme de la creme, deluxe, super deluxe mega system in my lab. And it would probably, the value of it would probably surpass $200,000 easily. But the important thing is that doesn't matter how deluxe it is, it's the same. The technique is the same. The only thing that it gives you is it gives you better coverage. For example, you have 128 electrodes instead of 6. So you have your head is full of electrodes. And you say, wow, full of it, but it's the same technique. It's exactly the same. So if you have 6 electrodes, if you have 128 electrodes, it just gives you better resolution. So back to resolution. So what's the spatial resolution? The spatial resolution of EEG ERP is a function of the number of electrodes. So the more electrodes you have, the better the spatial resolution is. But even if you had, how can you have 1,000 electrodes? Well, no, because the electrodes have a physical space, and if you need to put 1,000 objects on your head, they need to be sufficiently small. We don't have the technology today to position 1,000 electrodes in a meaningful way on the head, but we have technology to put 256 electrodes or 128. What I'll show you later is that at some point it makes no sense anymore because the electrodes begin to interfere with one another, and there's a physical size to these things, and the heads are also not infinite. So there's a finite space to put all this equipment on. We are very close to getting to that space. Spatial resolution of ERPs is on par or close to spatial resolution of PET, more or less. It's crude, but if you are close to the top, it's pretty good. If you're close to the cortex, it's pretty good. I would say, actually, I would revise what I said. It's slightly better than PET today, especially with dense array, when you have a lot of electrodes. Temporally, however, it's superior. Temporally, it's about 1 millisecond, at least in theory. It can go down to 1 millisecond because what it's looking at is it's looking at very, very quick electrical signals. And those electrical signals basically spark at the speed of light, at least theoretically. And with all the shifting that we're doing, we're able to see things that are happening within a millisecond or within 2-3 milliseconds. So in terms of time, it's great. And a lot of people are studying memory and visual processing and stuff like that with ERPs. It makes a lot of sense to do that because this is very sensitive in terms of its temporal resolution. As a matter of fact, a lot of people are using in concert EEG and fMRI, and that makes a lot of sense because then you can benefit from the temporal resolution of fMRI and of ERPs, the temporal resolution of ERPs, which is about a millisecond, and with the spatial resolution of MRI, which in certain fields can be a millimetric resolution. So in that case, you can actually say some interesting things, both in terms of the space and the time. Yes. So today we have technology. So there are 2 ways to get around it. That's an excellent observation. So there's several ways. There's several ways to get around this problem. One is to do the measurements separately, and then to put them together. So you do the ERP measurement separately, and you do the fMRI measurement separately, and then you bring them together using all kinds of tools that allow you to bring these 2 things together from a mathematical standpoint. The other thing is to do it concurrently, to perform these measurements concurrently. And for that, we have developed fiber optic ERPs. So everything here, everything in the system is actually not magnetizable. From the electrode through the cable, through everything is not magnetizable. These things cost a fortune, forget these numbers. And then you can actually perform ERPs together with MRI simultaneously. There are all kinds of technical difficulties, but it's doable. Then we have a technique like TMS. TMS is a slightly more brutal technique in the sense that it's very different from a conventional neuroimaging technique. It does something that is disruptive, and for many people, it's not considered a neuroimaging technique at all. But it's an interesting technique that is often used in conjunction with neuroimaging, or even without neuroimaging, it still rubs up against neuroimaging. TMS stands for Transcranial Magnetic Stimulation, is basically a particular device that you put close to the head and zap the brain with a strong magnetic field. The theory behind it is that if you zap the brain with a strong magnetic field, a very focal magnetic burst, the neurons that are immediately under that are going to get a shock, and as a result of getting the shock, they're going to be deactivated for a short period of time. They're going to be, if you want to think about it, they're going to be stunned. Okay, the neurons are stunned. They're going into a refractory period. During that time, they're not working. And because they're not working, you can sort of hypothesize that this is like a lesion. And you can actually see how the person is operating with a temporary lesion. This is a temporary reversible lesion because after enough time goes by, usually a few minutes or a few seconds, you're back to normal. You're back to your healthy self. Early TMSs were very crude, and they injected a lot of uncontrolled magnetic fields in all kinds of directions, and as a result, people had sometimes seizures, and all kinds of unpleasant things were happening. Today, the systems are much more refined. The chance of getting an ab reaction is very, very low. It always exists, but it's very, very low, and with the right screening, it's almost unheard of. So people who don't have any metal in their brains, that's obviously not good, but people who don't have a history of seizures and they're relatively healthy usually have no problem with these things. And the TMS is adjustable, usually up to 2 Tesla, sometimes a little bit more. So there's a knob and you can control how strong it is. And basically what you do is you start low and you go slow. So you increase slowly the thing until you see a response. So with TMS, you can actually give people a particular burst on a sweet spot, and their hand would jerk. And it's very interesting because when the hand jerks like that, when you give the burst and the hand jerks, you basically say, did you do that? And they say, no, I didn't do that. It's sort of happening to me, because they're not controlling it. It's happening to them. It's like a little electric shock that you give someone. So it's an interesting instrument whereby you can do there are all kinds of questions that you can answer by creating sort of a temporary or a transient lesion. Often what you can do is, if you're lucky, you can combine TMS with fMRI, for example. You can give somebody a transient lesion in the scanner, and you can see, as they are beginning to solve a problem, what's happening in their brain when they're trying to use that area and they can't. Some people have done that. This is very technologically challenging for all kinds of things, because when you give a TMS burst, the magnetic field is disrupted and it's not homogeneous anymore, but there are ways to do these kind of things. Another thing that you can do with TMS is you can actually do TMS with ERPs, which is a lot more common. You can do TMS with ERPs, and then you can see how people are coming back online, or what kind of, so for example, people with aphasia, you can actually create aphasia to people if you go to their spoken area. Healthy people, you turn them into neuropsychological patients. So these are healthy people, and you turn them into neuropsychological patients by giving them a particular deficiency, a brain deficiency, for a short period of time. So that's an interesting technique. We have another technique that is called MEG, that I'm going to show you here at the Neuro. MEG stands for magnetoencephalography, and that's actually, MEG is actually like the magnetic mirror image of ERP and EEG. MEG, it looks like a machine from outer space, because you have to have on your head like a whole house. So it's like you go into this chair, and there's like a whole house built on your head, which contains all kinds of sensors and stuff like that. And the chair can be either upright, or you can be a little bit reclined. But the interesting thing about MEG is that it's listening not to the electrical activity in your brain, but to your actual magnetic activity. So it's actually measuring magnetic field. As a result, for reasons that I'm not going to go into, it's a lot more sensitive than ERP. So ERP is a relatively crude instrument compared to MEG. MEG, the temporal resolution of MEG is the same as ERP. It's about a millisecond or so. But in terms of its spatial resolution, it's much better, and it can go much deeper. The signal is much smaller, so because that's the case, you have to build a whole special room with special isolation from the world. And you can't have radio waves in there and all that, so they have to put special materials in the walls. It's very expensive to do that. So MEG is also in the millions. To have a MEG device is in the millions. If you have access to MEG, it's really like you could ask very, very interesting questions. MEG is often used for things like default mode processing, although that you can also do with any of the other techniques. But the idea is that you put it together in a triangulate, like you triangulate these techniques. By triangulating these techniques, by using converging evidence, you take the advantages of one technique and you take the advantage of another technique, and you sort of do away with their disadvantages. Each technique has advantages and disadvantages. By triangulating them, you can sometimes confirm certain things that you see in different techniques time and time again, and you can disconfirm certain things that are only unique to a particular technique. Now, in the early days, people who looked at all this technology, people like Bob Uttal and other people, said, this is the new phrenology. What are you doing? This is like more and more and more and more technology that basically it's all the new phrenology. What are people doing with all these things? And the answer is yes, this is the new phrenology, absolutely. But it's got some interesting things that you can do with it. So for example, what you're able to do here that you couldn't do before is time course. For the first time, with things like MEG, with things like fMRI, with beginning to understand default mode processing, with beginning to understand, the difference between, by adding a temporal dimension to the spatial images, we're beginning to see how processes unfold in time, something that we couldn't do before. And we begin to see how things change in the brain as a result of particular cognitive processes. Before, we could only see states, sort of, and we didn't know how to connect them. And now we're beginning to, now we have longitudinal studies where we can see how people change. The same person changes over time. We can see, the value of MRI studies, by the way, has declined, as I mentioned to you, but it's very, very strong. I think that actually MRI is being undersold to people, because MRI and structural and volumetric studies are extremely important. Extremely, extremely important in order to understand, both psychopathology and healthy development. And if you look at all these things, and I just very quickly ran through, and I'm finishing, all these things. So, for example, if somebody wants to be a MEG imager, that's a whole world to itself. When I started out, for example, I started with ERP and EEG, then I went into MRI, then into fMRI, and optical imaging I did. By the way, optical imaging, one of the ideas behind optical imaging is that you can actually carry it on your head. You can put this equipment on your head and do some very difficult, like meditate, for example. So you can have the optical imaging on your head, and you can actually collect the information remotely. That's very easy. Today we can do it also with ERP, something that we didn't have before. We have wireless ERP today, something that we didn't have like 10 years ago. So the technology is beginning to get more and more mobile, more and more lighter, smaller, and it allows us to collect this information from people in a non-invasive fashion, or in a relatively non-invasive fashion, which is very important for field studies. Like if you're going out and if you need to go about. So today, EEG systems are very mobile. I mean, you take a suitcase or two suitcases with some batteries and some amplifiers and some electrodes, and you're all set. You collect the data, you go back to your lab, and you analyze the data for a few months, and you have you have the results. So it's very important to understand that whereas MRIs are very different. By the way, today even MRIs are becoming more mobile. Today they're building trucks, with big MRIs on them, and they're going and they're parking the truck somewhere in a place where there's no MRI, and they say, they make announcements before they say, on Tuesday we're going to have the MRI parked over there, and then all the people from the village are coming to get their brain scanned. This is getting more and more common, actually. And these kind of initiatives, you can't do it with MEG so much. You can't do it with MEG because it's so sensitive, but you can definitely do it with MRI. You can even do it with fMRI. You can even, to a certain extent, do it with PET. At Columbia, there's the first mobile PET. And it's extremely expensive, and when you go somewhere, it's not just parking the truck. You have to calibrate all the machines. It takes like 3 days to get the whole thing going, and these are not regular trucks. These are huge trucks, and they need liquid hydrogen in order to cool this. It's very, very complicated, but it's happening. It's beginning to happen. Like, you're beginning to see these imaging devices being mounted on trucks, and they're beginning to go around and stuff. It's inevitable that it's going. And the Jewish General Hospital just came out with this initiative for the Surgery Cruiser. I don't know if you saw that. There's the Surgery Cruiser. It's like, when I was a kid, when the ice cream truck would come around, you'll have the music, and you'll run, and get a. So now it's the Surgery Cruiser. If you're from the Jewish General Hospital, you just have to, walk around Montreal until you hear the Surgery Cruiser playing around a tune, and then you walk in and they perform minor surgery on you right then and there in the truck. So you just have to bring your Medicare card, and they'll do the surgery whether you need it or not, as long as you show up. So it's a very interesting concept that that you can actually go and get yourself like the medicine is coming to you, the equipment is coming to you. You don't have to go to the hospital. So I'll stop here, and if you have any questions or any comments about these things, I'm happy to answer.